is the last week of kinetics. Next week starts redox. That is when you will no longer be using math, and it will more be about you being able to recognize reactants and products, being able to recognize intermediates and catalysts, which is why we start with this one, because catalysts more have to do with reaction rate than anything else. And then working more on is something reducing something. Reducing, I always put it down into an acronym called OIL-RIG. Reduction is gain of electrons, and the oil part is oxidation, is loss of electrons. So if it's oxidizing, it's losing electrons. If it's reducing something, it's gaining electrons. I'm not going to go too much into that because that's the next 2 weeks. So that'll be next week. Again, you can always find the videos under the course tools. Please tell me if you cannot. I've been in ITAP, like I said, all this morning, and they still haven't told me how to get it off of the media gallery into the sections. I will figure it out eventually, but you might all be done with this course by then, and it will be pointless. Office hours are on Wednesdays at 8:30 as always. It's always wonderful to see people there, but of course, if you cannot make it to those office hours, we can schedule other times. It doesn't have to be at 8:30 in the morning, especially if you have long weeks. It can always be at some other time. Since I work until 9 p.m., it can even be in the evening, because I will be here, sadly. But would love to see a happy, friendly face. Okay, due dates. Everything is as it was, except for you have 2 worksheets due on Sunday. One is the half-life one, which of course you could do last week, but now you can do this week if you needed more time. And then there's catalytic converters. We're going to go through those types of questions in the recitation guide today, so don't worry. But please be aware that when we think about catalysts, we are talking mostly about speeding up the reaction rate by lowering the activation energy threshold. In which case I mean along the reaction coordinate, we're just making the bump shorter. That's all we're doing. So, the big thing that we can go on this week is kinetics in terms of the actual molecular level. Things hitting each other, things becoming another thing through that collision, etc. The thing that people don't realize is the reaction is to go forward. It has to not only collide, it has to collide with enough energy, and it has to collide in the right direction. What they mean by that is, if you have 2 positive things hit each other, they are not going to switch places. They're both positive. If a positive and a negative thing hit each other, like saying oxygen and a hydrogen, they're going to want to switch places because, and or take one away from another, etc. Whatever they want to do. That's because they'll have the right orientation. If they have the incorrect orientation, it will not happen. That is because, again, you have 2 similar forces, and therefore they'll just kind of dodge each other, or they'll like tap each other. Not enough energy, so it all ties in together. Those are the goals. You can write them down however you feel. Okay, activity 1. This is essentially trying to set up the 3 things you need to define collision theory. 1, they gotta collide. 2, they gotta have enough energy. And 3, they've gotta be in the right angle. Otherwise, it won't go forward. It's not gonna happen. All this through a PhET simulation. Activity number 2, seeing how reaction rate is dependent upon the concentration of your reactants and products divided by the change in time. So again, seeing how changing that concentration will overall change the rate of the reaction, which makes sense. I increase the concentration, I increase my probability of colliding with something else. If I threw 1,000,000 bouncy balls in here, a lot of them are going to hit each other. If I throw 5, we might be here a while. Okay. Finally, number 3, rate laws. So like I was saying over here on the board, not that anyone watching this video can see, maybe you should come to class, is that when you have something constant, we kind of ignore it. We're like, okay, that one's not what we're focusing on, we can just focus on this side. That is what it says by here, keep one reactant constant. So essentially, we kind of can ignore B because if we pretended that B was 1 molar for both of them, then we could say, okay, B is constant, so now we know whatever reaction rate change we see will be solely dependent on the change in A. So that's why I'd say keep one constant, figure out the rate orders for both of your things, A and B, C, and when you find those rate orders, then you can find the rate of the whole reaction, because once you know the rate orders, you can go back, plug in your rates, plug in a concentration for each, and you can find K, which is always good for a reaction. Some final things to note before going into the pre-lab. And also something to recap. Again, reaction coefficients, A, B, C, and D, that I did not list, unfortunately, are not equal to your rate orders. They are not equal. And then, what is a reaction rate equation? So sitting here, if it asks you, what is the reaction rate? I would say it's the change of a concentration over the change in time. And I would represent it like this, with delta. Delta being Greek for change. Also, the reaction rate is proportional to the number of collisions that happen over time. So it's not the number of moles per time, it's the number of collisions. And then it's the change in concentration, or the change of concentration over the change in time. Okay, these are all pre-lab questions. Any questions on that before we move on? Nope. Okay, we're going to move on to the, it shows up, recitation guide. Okay. So again, it says according to collision theory. I want to make this straight. Oh, there we go. Ooh. Collision theory. So again, like I said, number one, they gotta collide. If they don't collide, there's no collision to observe, so there's no theory. That makes sense. Next, gotta collide with enough energy. If there's not enough energy, they're gonna hit and bounce off each other and not do anything. Not what we want. We want them to hit with enough energy to switch partners and make a new product. Otherwise, doesn't matter. And finally, number three, they gotta collide at the right direction and or correct orientation. Right direction / correct orientation. If they don't do that, then you're going to get two things that are positive or two things that are negative, and they're just going to bounce away from each other. Why would something that's electronegative wants electrons fight with something that wants electrons when it can find something that wants to give electrons in the process? That guy's much easier to take electrons from. I'd rather mess with him than mess with another oxygen. That kind of thing. Okay. Which of the following conditions will affect the rate of the reaction? Okay, we know this from last week's lab. Anything to do with temperature is definitely going to affect the rate of the reaction. Again, it doesn't say increase or decrease. We're just looking at effect in general. Higher volume of reactants. Well, you and I know that changing a volume doesn't directly mean we're changing the concentration. We don't know if we changed the volume and changed the amount of moles that we put in. We just don't know. So that one is not directly going to affect the rate. We would need more information. Like, did you also remain constant moles so then the concentration changed? We just don't know. C, higher concentration. Well, there we go. We know that they changed the concentration, and that is definitely directly related to that overall reaction rate. As we saw before, that equals the rate. Presence of a catalyst definitely affects the rate. This lowers the activation energy and helps something move along faster. And then finally, granular size of the reactants. Again, as we know, the smaller surface area, the faster the reaction goes. If you did not get that question correct on the pre-lab from last week, let me know ASAP so I can put in those points for you. They should have gone back and what's it called? It's like reload the answers and everyone gets changed, but sometimes there's always a glitch. So go back and check and make sure that you got that one correct, and you were supposed to get it correct.
Did you check the top half or you tried to?
Top half. I went back and checked a few of them, and most of them seemed changed to correct. But again, just check for yourself, just in case I didn't check yours personally. Okay, so it should be decrease in temperature, a higher concentration, a presence of a catalyst, and then the granular size of the reactants, aka the surface area. All right, this next one is going to help us when doing the catalyst worksheet. So it says, for the decomposition of hydrogen peroxide in the presence of a catalyst. So next it's going to tell us two activation energies. So I'm going to write those activation energies next to the reaction that we're looking at. That way I know that is the energy barrier. Because when I'm looking at something like this, I'm going to be looking at this part right here, and that is going to equal the activation energy. This to this hill right here, that whole thing is the activation energy. So by writing down the activation energy, I know the amount of energy I need to get over the hill. If I can't get over the hill, I will not see a reaction form because they're going to keep falling back down the hill to the reactant side. So I'm going to go here. It says no catalyst is present. Without a catalyst, the activation energy is 75 kilojoules per mole. So I'm going to write that down so I know how many moles is for this reaction. This one says there is a catalyst, so it's going to be 56 kilojoules per mole. This one's without, so 75 kilojoules per mole. This one is with, so 56 kilojoules per mole. Okay, next, I need to now equate these reactions into the same unit. So I'm going to take these kilojoules and divide them by the amount of hydrogen peroxide so I know how much energy the whole system has. So here I take 65 divided by 1 and I get 65 kilojoules per mole. So here I'm going to go. My catalyst is not present, so the hilltop is going to be equal to 75 kilojoules per mole. My entire reaction only has 65 kilojoules per mole. So it's like it's going to be going up this hill and it only gets so far, and then it's going to slide back down. It just won't be able to make it over the hill. So the reaction would not occur. Okay? Does everyone see how we work that out? Makes sense there?
So if it's not higher than the catalyst present, it's not going to go over.
So the catalyst present, that is actually, so the catalyst is saying the activation energy. So that's how much this hill is. So we're saying the hilltop is at 75 kilojoules per mole. And now we're saying the reaction only has 65 kilojoules per mole. So it's just not enough to go over the hill. So it's not that the catalyst has that many, it's actually that the activation energy is that tall. Does that make sense? The catalyst, of course, follows this line here. And so that's why we equate the two. Does that make sense? All right, next one. This reaction also has 65 kilojoules per mole. But now that there is a catalyst present, this hill is only 56 kilojoules per mole tall. And so then when I'm going up, I have 65, so I can definitely go over that hill, so that reaction will definitely happen. Next, I'm putting a lot of energy in there, but I am dividing it by 2 moles, so it takes about 2 moles of hydrogen peroxide. And when I divide those together, I get 77.5 kilojoules per mole. So again, because I put in so much energy, even though there's not a catalyst present, it just barely gets over the hump. And that's because, again, we put in a lot of energy. And finally, I take 24 kilojoules per mole, so not a lot of energy going in here, but only you needed to use half the moles, so that's pretty good. And I get 48 kilojoules per mole. So with that, because I didn't put in enough energy, even though there's a catalyst present, it still doesn't make it over the hill. So this one does not go through. Does that make sense to everybody? Okay. You see how to do that math? It's not hard, right? Okay. In the diagram below, we're just going to label the reactant. Reactant's always at the start. So this is my reactant. Check. I need to label my product. The product is always at the end of the reaction. That's what we get. So this is my product. Check. Transition state. When we go from reactants to products. So what I would say is this is reactants, this is products. So the peak of this is going to be where we're transitioning between the two. Everyone see that? That makes sense? Activation energy. Activation energy is how much energy we need to go from reactants to products. And so that means it's always going to be the amount of energy from the start all the way up to when we're transitioning. So activating the entire reaction. So this right here where we always go E with the lowercase a, that is our activation energy. And then finally, we say, okay, and the enthalpy of the reaction. So the enthalpy is actually equal to the amount of energy that is either released or it's absorbed in the entire reaction. And so it's a difference between products and reactants. And so it's always going to be equivalent to, from the product line to the reactant line of energy, and that will be our change in enthalpy. Okay? So again, like I said, if we want to know if it's negative or positive, well, the change in enthalpy equals products minus reactants. And here I can see that if I put arbitrary numbers, this is increasing as we go up. So this is like 3, and we'll say this is like 7. So if I take 3 minus 7, I get negative 4 kilojoules per mole. And that makes sense to us because when we think about it, if the energy of the reactants is greater than the energy of the products, then the energy must be being released. Because it means that whatever's left behind doesn't have that energy. It's less than what we started with. And that energy is always lost as either heat or light or smoke or gas or something. And so it's lost into the system. So the energy was released into the universe. And in doing so, that means that it's an exothermic.
Wait, how do you know it's releasing again?
Because we have our products here that have less energy than what we started with, our reactants. And so what we start with has more energy than what we end with. The energy must have been released. If we go the other way, if our products, say, had more energy than our reactants, then that would mean that we started with less energy and ended with more, so it must have been absorbed into the system. So we have to get it from somewhere. As we know from physics, law number 2, energy cannot be created nor destroyed, just as matter cannot be created nor destroyed. All right, we ready to move on to some fun, we hope? We're going to go back to labeling, my favorite thing. Ooh, if we can see. Oh. I don't know how to block this. Oh, all the way to the top. Okay. So, this says G. I know from just now. Ooh. Okay. So G is our reactants. On this side, I know the transition state. Up here it says, wait for it, F. So that's my transition state. My coordinates, reaction coordinates, is where the reaction goes forward. This is marked as B. So I know reaction coordinate is B. Let it come back to center here. Products are at the very end. This is H. So I'm going to write my products are H. When I think of catalyst, I think of in a reaction coordinate thing where I have my reaction coordinates down here. I have energy here. I would think of a catalyst as being shown like this, where that is the catalyst. Let it load. And I don't see that on this graph. It only has one reaction profile. And so with that, thank you. Oh, there we go. It's too much light. I'm too excited about this one. So with that, I don't see anything that suggests a reaction to be having a lowered activation energy. So there's no catalyst in here. Next, it says an intermediate. Well, an intermediate on this kind of reaction coordinate graph would look a little something like this, where this is reactants, this is the intermediate, this is the transition state, and that's the products. I don't see that either, so there's no intermediate. Enthalpy change, as we know, is going to be the difference between the products and the reactants, so that is E. Entropy change cannot be seen. Entropy is actually something that you have to experimentally find with Gibbs free energy, the enthalpy, and the temperature. So we can't find that in this one, so entropy change is not findable. Energy, as we know, is what is on the y-axis. We can see that. Which is A on this side, so A is energy. Oh, there you go. I have to go deep in here. And then finally, activation energy of the forward reaction is when we're going from reactants to our transition state. So here that is C. And then it says activation energy of the reverse. So that is when you're going from products to your transition state. And here they've marked it as D. Okay? Does everyone see that now? It's done changing its color. So the biggest thing to see is activation energy of the reverse is actually the difference in energy from the products to the transition state, F, while the activation energy of the forward way is going from products, reactants, G, to F, the transition state. Does that make sense? So the activation energy of the forward reaction is that one, and of the reverse is actually the products minus that transition state, which is going to help us for number 6. So number 6, it says the activation energy for the following reaction is 432 kilojoules per mole. What is the activation energy for the reverse reaction? Well, like I said, the activation energy of the reverse is going to be equal to the energy of the products minus the energy of the transition state. And these are always going to be the enthalpy change, because that's, again, our products, and our activation energy. So, I put EA, I might just put E. So with that, I'm going to say, okay, I take the energy of the products, which is my enthalpy change, so that's negative 164 kilojoules per mole, subtract my 432 kilojoules per mole, and that is going to equal negative 596 kilojoules per mole. Okay? So again, activation energy of the reverse is just the products, H, minus the activation energy, and or the energy of the transition state, which is all the way there at F. Do you see that? Pretty good? All right. Easy math. Okay. Identify all the intermediates. So, when we're identifying the intermediates, we're essentially looking for something that didn't make the final cut in the total reaction. And so when I look here, I see I've got 1, 2, sorry, my final reaction, if I wrote everything down, would be 2NO2 plus NO3 plus CO is equal to NO plus NO3 plus CO2 plus NO2. And instead I have no NO2 on this side, only one NO2, so I know that this NO2 is an intermediate. It disappears on either side. NO2, NO2. So there's one intermediate. Another thing that doesn't show up in the final equation at all is this NO3. So now I know this NO3 is my other intermediate. And then I look at the reaction at 1 NO2, that's good. CO's left, that's good. CO2 and NO. Everything else is made it. So all of these are intermediates because they didn't make the final cut. It means that they were used up in the reaction and or changed into different things in the reaction and then were used up. And either way, their reaction has been used up. So they were an intermediate to make the final. Does that make sense to everybody? So if you're ever looking for an intermediate, just look for something that's not in the final. And if you're looking for a catalyst, say cesium, what you're going to look for is it's going to make the cut in both ways. What I mean by that is that you're going to see it as a reactant and as a product. It will not be consumed. It will be used to lower the activation energy, and that's it. So that's why cesium would be a catalyst. Okay, final thing on this page, and then we move on to our last question. So I have, why can a catalyst increase the reaction rate? Okay, catalysts, like I said, are usually a metal ion like cesium, you know, something nice and small. Other times they can be CO2 in some cases. People like a little bit of carbon dioxide, stuff like that. What they do is lower the activation energy. They do not increase or decrease temperature. That is not their job. They do not change the surface area. They're not some magical punching bag that reduces everything to rubble. They're in and of itself literally something that alters the reaction mechanism in order to lower the activation energy. That's all they do. Nothing else. We don't know why they work that way. It's something that many people are still looking at. They're wondering, why do catalysts lower the activation energy? Because they don't change the temperature, they don't change the surface area, they don't change the concentration. So we don't understand that part. And yet they work so well. Things like uranium fluoride, which are fun to work with, stuff like that. It burns bright green and makes you question how safe it is to be open. All right, final thing. We're going to draw a reaction coordinate diagram. It says we're going to draw one for an endothermic reaction. Whenever I see them say endothermic, I automatically draw the reaction coordinate system. I don't even wait to see what the rest is about. Hold on, I think it's this one. Hold on. So, I don't even wait to draw what's on either axis. I just know endothermic means that the reactants have less energy than the products. And so I'm going to draw that immediately. I'm not going to wait. I'm not going to question it, because if I do anything else before that, I'll mess it up in my head. I know this for a fact, so I'm moving on. It says with or without a catalyst. And I know this will be without a catalyst, so that one will be with. So without catalyst, with catalyst. Great. Next. So I've done with and without in one diagram. Label each axis. So I know this is the reaction coordinates and or how the reaction progresses. So I know that's my x-axis. I know that my y-axis is energy. So I've done that. Activation energy. We have 2. So again, that's my reactance line. This is the activation energy for with a catalyst.
Okay, I thought this was going to minus TSA.
You're good, yeah. And then this is activation energy without a catalyst. So I've got 2 in here. Just remember to draw them both because you have 2 different profiles. And then finally, it says reactants and products. And as we know, these are reactants and this is our products. Again, for a sanity check, my change in enthalpy is going to equal products minus reactants, always. Here we go. Let's show you. Okay, here we go. Products minus reactants. So if I use the same numbers, like this is 3 and this is 7, if I do something like this equals 7 minus 3, this now equals a positive 4 kilojoules per mole. And since it is positive, that means it is then endothermic because it means energy was absorbed in the in this reaction. There we go. Okay, so everybody see this? It's all good? Okay, thank you so much. I'm going to end this here because this is the last question, so I have nothing else for you. I'll see you guys next week. Now I'm ready to answer all your questions about the pre-lab, the lab, the quiz, the homework, whatever you feel. All right. Just as the